Have you ever dropped your phone and watched the screen shatter into a million tiny pieces? Or have you seen a car bumper get a little dent after a minor bump, instead of breaking apart? The difference between these two outcomes comes down to a property we call impact toughness. It's not just about being strong, it's about being able to absorb a sudden shock or blow without fracturing. Think of it like this. A material might be very hard, like glass, but it's not very tough. A single, sharp impact can cause it to fail completely. Toughness is a material's superpower to bend, deform, and soak up energy when something hits it unexpectedly. It's the resilience that keeps things from snapping in two when life throws a curveball or a baseball at them. This idea of toughness is incredibly important in the world around us, a world built from all sorts of materials. Engineers and scientists are always thinking about how the things they design will behave under stress. Will a bridge hold up against strong winds and the constant rumble of traffic? Will a playground swing set be safe for kids who might bump into it? These aren't just small questions, they are critical for safety and reliability. A material that can't handle a sudden impact is a liability. It could lead to catastrophic failures, whether it's a structural beam in a skyscraper or the plastic casing on a power tool. Understanding a material's toughness helps us predict how it will perform under real-world conditions, ensuring our creations are safe and last a long time. So how do we measure this invisible but vital property? We can't just look at a piece of steel or plastic and know how tough it is. We need a way to test it, to put it through its paces in a controlled scientific way. This is where impact testing comes in. Scientists have developed brilliant methods to apply a sudden, forceful blow to a sample of a material and measure exactly how much energy it can absorb before it breaks. It's like a mini, super-fast crash test for materials. By doing this, we can assign a number to a material's toughness, allowing us to compare different plastics, metals, or composites and choose the best one for a specific job. It's science in action, helping us build a safer, more durable world. Think about all the things you use every day that need to be tough. Your bicycle helmet, for instance, is designed to absorb the energy of an impact to protect your head. The landing gear on an airplane has to withstand the massive shock of touching down on the runway. Even something as simple as a plastic storage container needs some toughness so it doesn't crack when you accidentally drop it. All these products rely on materials that have been carefully selected for their ability to handle sudden loads. Without a way to measure impact toughness, designing these items would be pure guesswork. It's a fundamental concept that bridges the gap between the materials in a lab and the functional, reliable products that make our lives better and safer. Now that we know what impact toughness is and why it's so important, let's meet the two heavyweights of the testing world, the Izod test and the Charpy test. These aren't people, they're standardized methods or procedures named after the brilliant engineers who developed them. Think of them as two different obstacle courses designed to push a material to its breaking point. Both tests are famous in the fields of engineering and materials science, and they have been used for over a century to help us understand how materials behave. They are the gold standard for measuring impact strength, providing the crucial data that engineers need to build everything from pipelines to prosthetics. Their goal is simple: hit a material and see how it holds up. The Izod, pronounced Izod, impact test is one of our main contenders. It was invented by an English engineer named Edwin Gilbert Izod in the early 1900s. The Izod test is particularly popular for testing plastics and other polymers, although it can be used on metals as well. Imagine you have a small, rectangular bar of the material you want to test. In the Izod method, you clamp one end of this bar vertically, kind of like a tiny flagpole. It stands upright, ready to face the challenge. This setup is a key feature of the Izod test, and it influences how the material experiences the impact. It's a classic, reliable method that has given us decades of valuable information about the toughness of countless materials we use every day. On the other side of the ring, we have the Charpy, pronounced Charpy, impact test. This test was developed by a French scientist, Georges Charpy, around the same time as the Izod test. The Charpy test is the go-to method for testing metals, especially steels used in construction, shipbuilding, and pipelines. In this test, the rectangular sample bar isn't clamped vertically. Instead, it's laid down horizontally and supported on both ends, like a miniature bridge. This simple difference in how the sample is held is what makes the Charpy test unique. It simulates a different kind of impact scenario, one where a material is struck in the middle while being supported at its edges. Both of these tests, Izod and Charpy, are like the ultimate stress test for a material. They are designed to find a material's breaking point in a very specific, repeatable way. By having these standardized methods, an engineer in Japan can get the same reliable results as an engineer in Germany or Brazil. This global consistency is what makes these tests so powerful. They provide a common language for talking about toughness. When a company says their new polymer has a certain Izod impact strength, engineers everywhere know exactly what that means. So let's get ready to see how these two legendary tests go head-to-head in our scientific showdown. So, how do we actually perform these tests? At the heart of both the Izod and Charpy tests is a very simple yet brilliant piece of equipment, a swinging pendulum. This isn't the kind of pendulum you'd find in a grandfather clock. It's a heavy, weighted arm designed to deliver a powerful, precise blow. The science behind it is wonderfully straightforward. Before the test begins, the pendulum is raised to a specific known height. Because we know its weight and how high it is, we know exactly how much potential energy it has stored up. Think of it like pulling back a slingshot. The farther you pull it back, the more energy it has. It's all based on the laws of physics. When the test starts, the pendulum is released. It swings down in a smooth arc, gathering speed and converting its potential energy into kinetic energy, the energy of motion. At the very bottom of its swing, where it's moving the fastest, the pendulum strikes our small, prepared sample of material. This is the moment of truth. The impact is sudden and forceful. The goal is to break the sample with a single blow. The energy from the pendulum is transferred to the material sample. If the material is tough, it will absorb a lot of that energy as it bends and fractures. If it's brittle, it will snap easily without absorbing much energy at all. After striking and breaking the sample, the pendulum doesn't just stop. It continues to swing up on the other side, but it won't reach the same height it started from. Why? Because some of its energy was used up, absorbed, by the sample when it broke. The tougher the material, the more energy it absorbs, and the lower the pendulum will swing on the other side. The testing machine has a scale that precisely measures how high the pendulum swings after the impact. By comparing the starting height to the finishing height, we can calculate exactly how much energy was lost. That lost energy is the impact energy, the value that tells us how tough the material is. To make sure the material breaks in a predictable spot, we use a special sample. The small bar of material isn't just a plain rectangle, it has a tiny notch cut into it. This notch, which can be V-shaped or U-shaped, creates a point of stress concentration. It's like a pre-made weak spot that directs the fracture. This is important because, in the real world, materials often fail at places where there are small imperfections like a scratch, a sharp corner, or a microscopic crack. The notch in our test sample mimics these real-world stress concentrators, giving us a more realistic idea of how the material will behave when it's not perfect. It's a clever way to ensure the test is both repeatable and relevant. While the Izod and Charpy tests have their unique styles, they share a lot of common ground. You could say they are more alike than they are different, especially in their fundamental purpose and principles. First and foremost, both tests are designed to do the exact same thing, measure the impact toughness of a material. They both answer the question, how much energy can this material absorb from a sudden blow before it fails? This shared goal makes them brothers in the world of material science. They both provide a numerical value, usually measured in joules or foot-pounds, that quantifies a material's resistance to fracture under high-speed loading conditions. This number is the key piece of information that engineers are looking for. Another major similarity is their reliance on a notched sample. As we discussed, both tests use a small standardized bar of material with a carefully machined notch cut into one side. This notch is not an accident, it is a crucial part of the experimental design for both methods. The presence of the notch creates a stress concentration point, ensuring that the fracture will start there, and that the test results are consistent and repeatable. Without the notch, the material might break at any random point, or it might not break at all, making the results unreliable. This shared feature helps to simulate how materials with real-world imperfections like sharp corners or tiny cracks might fail under stress. The core mechanism of both tests is also identical: the swinging pendulum. Both the Izod and Charpy testing machines use a weighted pendulum raised to a specific height to strike the sample. The physics behind the measurement is the same for both. The energy absorbed by the specimen is calculated by comparing the pendulum's starting energy to its energy after it has broken the sample and swung past it. This principle of energy conservation is the scientific foundation upon which both tests are built. The higher the energy absorbed, the tougher the material, regardless of whether you are using an Izod or Charpy setup. It's an elegant and effective way to get a direct measurement of toughness. Finally, both tests are incredibly important for ensuring safety and quality in manufacturing and construction. They are standardized by international organizations like ASTM, the American Society for Testing and Materials, and ISO, the International Organization for Standardization. This means that the procedures for preparing the samples, running the tests, and reporting the results are strictly defined. This standardization ensures that a Charpy test performed in one country can be directly compared to one performed in another. This global consistency is vital for international trade and for building large-scale projects like bridges or airplanes, where components might be sourced from all over the world. Both tests are indispensable tools for quality control and failure prevention. Despite their many similarities, the Izod and Charpy tests have some key differences that make them suitable for different materials and situations. The most obvious difference is the orientation of the test sample. In the Izod test, the sample is held vertically, clamped at one end like a cantilever beam. The pendulum strikes the sample on the same side as the notch, a short distance above the clamp. In contrast, the Charpy test places the sample horizontally, supported at both ends like a simple beam. The pendulum strikes the sample directly in the middle, on the side opposite the notch. This fundamental difference in how the sample is held and struck means the material experiences different types of stress during the impact. Another important distinction lies in the notch itself. While both tests use a notch, the shape and dimensions of the notch can differ. Charpy tests typically use a V-notch or a U-notch, sometimes called a keyhole notch, with the V-notch being the most common for testing steels. The Izod test also uses a V-notch, but its dimensions, particularly the radius at the bottom of the notch, are specified differently. These subtle variations in the notch geometry can have a significant effect on the test results, as a sharper notch creates a higher stress concentration and can make a material appear more brittle. This is why it's so important to specify which test and which notch type were used when reporting results. The type of material being tested often determines which test is used. The Charpy test is overwhelmingly the preferred method for metals, especially steels used in structural applications, pressure vessels, and pipelines. Its simple beam setup is considered more representative of the stresses these materials might face. The Izod test, on the other hand, is much more commonly used for testing plastics and other polymers. Because plastics are often molded with sharp corners or other features that act like stress concentrators, the cantilever setup of the Izod test is seen as a good way to evaluate their notch sensitivity. There's also a regional preference. The Charpy test is more dominant in the United States, while the Izod test has historically been more popular in Europe. Finally, the equipment and the energy ranges can differ. While both use a pendulum, the size and weight of the pendulum can be different, leading to different impact energy capacities. Charpy machines are often built to deliver very high impact energies, which is necessary for testing tough steels that can absorb a lot of energy before they fracture. Izod testers, particularly those designed for plastics, often operate at lower energy levels. The clamping mechanism is also a point of difference. The Izod tester requires a robust vise to hold the sample securely in its vertical position, while the Charpy tester uses a simpler anvil to support the sample at its ends. These equipment variations reflect the different applications for which each test was originally designed. These tests might sound like something that only happens in a high-tech laboratory, but their results have a huge impact on our everyday safety and convenience. Let's consider the bumper on a car. Its job is to absorb the energy of a low-speed collision to protect the more expensive and critical parts of the vehicle, like the engine and the frame. Car manufacturers need to choose a material, often a tough plastic or a composite, that can take a hit without shattering. They would use a test like the Izod impact test to compare different types of plastics. A material with a high Izod impact strength would be a great candidate because it can deform and absorb a lot of energy, resulting in just a dent instead of a pile of broken pieces. Now think bigger. Let's talk about a massive steel pipeline carrying natural gas across a cold, remote landscape. The steel used for this pipeline must be incredibly tough. In a cold environment, some metals can become brittle, meaning their ability to absorb impact energy drops dramatically. A small crack could potentially grow and cause the entire pipe to rupture, leading to a dangerous and costly disaster. To prevent this, engineers rely heavily on the Charpy V-notch test. They test samples of the steel at very low temperatures to ensure it remains tough and ductile even in the harshest conditions. The Charpy test provides the critical data needed to select a steel that will keep the pipeline safe and secure for decades. The importance of these tests extends to countless other areas. In the world of sports, the materials used for helmets, whether for football, cycling, or hockey, are rigorously tested to ensure they can absorb the shock of an impact and protect the wearer from head injuries. In construction, the steel beams and bolts used to build skyscrapers and bridges must have a proven level of toughness to withstand forces like wind, earthquakes, and the daily load of traffic. Even the plastic casing on the power drill you use for home projects has been tested to make sure it won't crack and expose the electrical components if you accidentally drop it. Ultimately, these tests are a bridge between scientific theory and practical, real-world application. They give us confidence in the materials we use to build our world. When an engineer designs a new product, they aren't just guessing which material will be strong enough. They are using the data from standardized tests like Izod and Charpy to make informed decisions. This data allows them to compare materials, predict performance, and set quality control standards for manufacturing. It's a quiet but constant process of testing and verification that happens behind the scenes, ensuring that the products we rely on every day are not just functional, but also safe and reliable. So after this showdown, which test is the winner? The truth is, there is no single winner. The choice between the Izod and Charpy test isn't about which one is better overall, but which one is the right tool for the specific job at hand. The decision depends largely on the material you are testing and the standards you need to follow for your industry. It's like choosing between a screwdriver and a wrench. Both are excellent tools, but you need to pick the one that fits the fastener you are working with. The key is to understand their strengths and apply them in the right context. If you are working with metals, especially steels for structural applications like bridges, ships, or pressure vessels, the Charpy test is almost always the way to go. Its simple beam setup and widespread use in metals standards make it the industry benchmark. It is particularly valuable for what's called a ductile to brittle transition temperature test, where samples are tested at various temperatures to find the point where the steel loses its toughness. This is critical information for any steel structure that will be exposed to cold weather. So, for the world of heavy-duty metals, Charpy reigns supreme. On the other hand, if your world revolves around plastics, polymers, and composites, the Izod test is often the more common choice. The cantilever beam setup is considered very effective for evaluating the notch sensitivity of these materials, which is a major factor in how plastic parts fail. Many product specifications and quality control procedures in the plastics industry are written around Izod impact strength values. So if you're designing a plastic phone case, a car's interior components, or any other molded plastic part, you'll likely be reaching for the Izod test to verify your material's toughness and ensure it meets the required performance standards. In the end, both the Izod and Charpy tests are indispensable heroes in the field of materials science. They provide a simple, reliable, and standardized way to measure a property, impact toughness, that is fundamental to the safety and durability of the world we have built. They allow us to push the boundaries of engineering, creating materials and products that are stronger, lighter, and more resilient than ever before. So the next time you see a structure that withstands the forces of nature, or use a product that survives an accidental drop, take a moment to consider the science. Somewhere in its development, a small, notched sample likely faced off against a swinging pendulum in the ultimate impact test showdown.